Alright, we are going to very soon give away our drone, which we believe flies, but maybe a rolling one. Okay, you got to put your business card in that bowl. Please don't leave it on the floor. Oh, you're filling it out. That's okay. When you're done filling it out, please pass it back. Put your business card in there. If you don't have a business card, you can draw your own business card on those sticky notes. We don't give you for effort, so if you get like really creative, it's cool, but you still might not win. But whoever throws their card in there has a chance to win. Please keep that moving around the room, and we will get started right now. There is one empty seat here. Somebody abandoned it. Oh, sorry, I'm giving away your seat. It's the last seat in the house.
Is it anybody?
Oh, no, it's yours. Okay. Yeah.
No, it isn't.
Okay. Our speaker this evening has 15 plus years of experience, holds 8 patents, and formerly worked for both Nokia and Sun Microsystems. Please welcome the CTO of NuoDB, Seth Proctor.
Hey, in the back, can people hear me at this volume? Good. First of all, thank you for coming here tonight. This is great to be speaking to such a full room, such a lively room. This is great. Also, thank you for taking our T-shirts. Knox in the back of the room particularly thanks you because he did not want to have to carry them home. So there are more. Please come up after the talk and feel free to grab one if you didn't get one or if you got the wrong size. In addition to making T-shirts, at NuoDB we also do a database. And I'm actually not going to talk a lot about. Okay, so the real question is how many times I'm going to trip over these tables tonight. I'm not going to talk a lot tonight about our database specifically. I'll be around afterwards. I'm happy to talk about what NuoDB is. I will come back to it a little bit at the end of the talk. The short version is what we built at NuoDB is a relational database. Believe it or not, SQL became so uncool that it's come back around now and it's like hipster cool again. So we're glad, rarely am I on the front end of a trend, so I was kind of excited when that happened. We are a relational database that does all the things that a SQL database should do: multi-way joins, massively complicated transactions, views, store procedures, yada, yada, yada. But designed with the assumption that what people are building today are distributed architectures. We've done client-server for a long time. We're now thinking about distribution. We're thinking about cloud, and that's the set of problems people want to solve. And that's what we've done at NuoDB. And what I'm going to talk about tonight is less NuoDB specifically and more what I think that means. You heard earlier, I was at Nokia. I was at Sun for a very long time. For those of you in the room who have been in the computing industry for more than a few years, cloud is not really a new thing, right? It's just a new name. We've been doing grid computing, horizontal scale, on-demand computing, all kinds of different words for kind of similar concepts for a very long time. And so cloud, to me, on the one hand, there's a lot of buzz around it. There's a huge hype curve. On the other hand, I think there actually are interesting architectural issues that come up when you start talking about cloud. And I think, to me, that's kind of where the interesting definitions come from. When I talk about cloud, it's not about, is this public cloud or is this private on-premise? Does it have to be Amazon? Does it have to be OpenStack? Does it have to speak a set of protocols? To me, when you're talking about cloud, you're talking about a set of architectures and a set of problems you're trying to solve. And that's really what I want to talk with all of you about tonight, is kind of where I think that comes from. And particularly in the data management space, why that's challenging. Why kind of the approaches that we've taken for the last 10 years, taking those client-server models and trying to retrofit them into this new set of problems only gets you so far. And hopefully convince you all that those of us who have spent the last 5 or 10 years kind of stepping back and fundamentally rethinking architectures weren't totally crazy. A little crazy, maybe, but to survive this winter in Boston, you had to be at least a little crazy. So that's really what I want to talk about tonight, is what is unique about cloud, what I think that is, and why we've done what we've done at NuoDB. What do I think cloud means? I think it means many things, but I think there are a couple of common threads when people talk about cloud architectures that are really important, right? And if you've gone onto Amazon, you've experienced this. If you've tried to run OpenStack, you've experienced this. But if you've just tried to spin up some virtual machines, and like get them running on a new server, right? Or you've tried to run Docker, or you've tried to do kind of anything where you're running something in a slightly more agile format than you've done before. You've kind of gone through this set of issues before, right? What I think people mean when they're talking about cloud architectures, first, I think everyone's talking about on-demand capacity, right? Pay for what you want. Get resources online when you need them, shut them down when you don't, right? And I think that's really one of the reasons that Amazon is so wild. Did everyone see their numbers last week? Like $5.1 billion and growing at 50% a year? I mean, damn. Anyway, sorry. If you haven't seen it, Amazon, like last week for the first time, was like actually had to announce their numbers, and they're kind of huge. But that's kind of, when you look at Amazon as a dev test environment, that's part of what makes it so powerful. It is so wicked easy to get on there and just spin up an instance when you need it, shut it down when you don't, add a few more, go to another region, spin some things up. Right? That's one of those really powerful ideas of cloud. It's this like infinite pool of resources at your disposal. Whether that's public infrastructure or not, what that really means is there needs to be a model for dynamic provision. Right? There needs to be a way to get at those resources, to get things, and that gives you flexibility. Right? That gives you the ability to get things when you need them. That gives you the ability to program the model you need kind of operationally. And increasingly, the way people think about that is more and more towards commodity. Right? One of the things that people associate with cloud is getting away from those big, vertically scaled systems that we certainly did at Sun, that other people did for years. Right? You don't go faster today or handle more capacity by deciding to buy like a bigger refrigerator and waiting 6 months for it to show up. Right? You do it by spinning up a few more machines. My CTO and I have an argument about this all the time. He likes to say, you want to go faster, add more machines. And I'm like, no, you want more throughput. It's different. Really? It's going to be that kind of night, huh? Okay, good. That's good. That's kind of expectation setting. Thank you all, I appreciate it. But like, I think that's important, right? That notion of being able to get to commodity infrastructure, but be able to solve all of those enterprise scale problems, right? And to me, another thing that's great about cloud that's not on this slide is it's very democratizing, right? It's like, I love hacking on giant servers when I was at Sun. But I love the fact that today I'm not a Sun employee and I can still hack on giant systems. And it's because I can get to that kind of capacity. And we're building models based on this kind of demand model, not on having to be one of the few people who can get on one of these big systems. Big systems will always be here, right? The heat death of the universe, there will still be like mainframe systems and they'll keep going, right? I mean, that's just kind of the reality of our community today. But increasingly, that's not where we are, right? And increasingly, that commodity model doesn't just mean cheap. It doesn't just mean kind of easy to get to, but it means hybrid, right? It means I'm going to run things that might be in my data center and in a public cloud, or might be in multiple public clouds, or might be just in my data center, but on different kinds of machines with different kinds of resources, right? Why? It's cost effective, lets me solve problems efficiently, it doesn't make me worry about the next upgrade cycle, right? Again, it's that I can get things when I need them and shut them down when I don't. And how do you make all that work? This is one that we sometimes lose track of, right? But as you build these increasingly complicated systems, you need to think about simplicity, right? Because when you start talking about, well, I've got 10,000 nodes running and it's across 7 Amazon regions and I'm running 4 different OSs across 10 different data types and I'm using EBS and S3 and Glacier and everything else, and suddenly you're like, well, I have no idea what's going on, right? And so that's why when Netflix talks about being wildly successful, the way they've done it is they've built all of these tools on top of it to abstract, to simplify, to make it possible to actually manage at this scale, right? So when we're talking about cloud, we're also talking about increasingly moving towards simplifying the programming experience, the operational experience, the ability to understand what you have. And that's really one of the core ideas that we're going to talk about today, is why I think rethinking core architectures for data management is so important, because that's what gets you to those much simpler models. And you see this everywhere, right? You see this with monitoring APIs, you see this with management APIs, you see this with the tools we build. I'm sure everyone in this room has at least some exposure either to like being pleased with the simplicity of something, or being infinitely frustrated with the fact that it feels like you've got great resources on hand, but you can't do anything. I won't cause people to date themselves by raising their hand, but if you ever did MPI C programming, and you were really frustrated that like your Fortran program or your C program or whatever was getting like 20% cycles across a cluster, like that's what I'm talking about, except now it's all JSON instead of something, I don't know, whatever the kids are using now, I can't keep up with it. And resiliency, right? Resiliency. This is one of those things that I think is one of the real promises when people think about cloud computing, right? Is that if I run in multiple places, that I can sustain failures, right? My service as a whole can keep going even as I lose pieces, right? And if any of you in this room is from the telecom industry, right, you can replace the word cloud architecture with telecom architecture, and like a lot of this just works, right? Because like, why is there a dial tone 100% of the time you pick up? Okay, so for people who don't know this, there used to be these things called phones sitting like on a table, and you picked it up and it was like beep, 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 you know, the dial tone, right? Seriously, you joke, but like I recently was doing this in like for a university audience, like a whole blank stares, and I was like, you know, the dial tone. Like when you pick up your phone, they're like, I was like, all right, I hate everyone in this room now. But like, the dial tone is always there, and it has to always be there, right? And the reason it's always there is because this is the same design methodology, right? You don't design with redundancy. You don't design with like another copy of something you can fail over to. You design assuming things will fail, assuming there's like mad complexity. You build abstraction layers on top of it to make it simpler to work with. You build systems that by their nature, not just are redundant, but are able to react to failure and get themselves back into a working state. And then you have a dial tone. You have a thing that is always there, right? And in the telecom industry, that's just like, that's taken for granted. And the computing industry, we're kind of starting to get spoiled enough by public cloud that we're getting there. And this is like one of those cases where I think getting spoiled is actually really good, right? Because it's kind of making us all raise the bar a little bit higher and say like, wait, that's what I really want. Like, I don't want to have to be a Fortune 100 company to get this. Like, I want that to be the baseline for my startup. I want that to be the baseline for any new thing I'm building today. It should never go down. It should always be there, right? The platform layer should always be there. And that's really like when we talk about benefits, like why we're doing all of this cloud nonsense, right? We're talking about being able to handle greater capacity, but do it in a cost-effective fashion, right? We're talking about higher availability and better failure handling because everything's automated, everything's monitored, right? Everything is designed with this failure model in mind. Commodity is great, except guess what? There's a reason it costs less. Like, it fails. You know, I mean, seriously, when you spend like $1,000 for a disk or you spend $100 for a disk, part of that's the name brand and the hype, and like people have been fooled into buying $1,000 disks for 30 years. But there we go, failed and it came back. Hooray! Part of it really is that like, you know, the mean time between failures are radically different, right? Or the temperatures that this can sustain, or like the other weird things that you don't expect, right? The error correction, things like that. So when you talk about commodity, great, things are cheaper, things will fail much more frequently, right? And so we're building systems with that in mind, and that's starting to bubble up past kind of core infrastructure to software services we're building, which I think is a really good thing. Another benefit that I'm going to talk about a little bit later is that increasingly we're taking all these ideas and we're expanding them beyond the data center, right? And we're really thinking about global operations, and that gets really interesting, right? So I'm going to come back to that one. What are the challenges, right? Anyone in this room who's ever studied distributed systems or thought for like maybe 2 minutes about the challenges involved in like getting something off your laptop and onto say more than one machine, right, has appreciated that it's an exercise in trade-offs, right? And later on I'm going to define what I think a distributed system is, but the other definition possibility is it's an exercise in trade-offs. And when you decide to distribute something, it brings challenges. It brings a lot of great benefits. It also brings real challenges, right? And some of them, lots of failures happen with greater frequency in crazy, crazy ways. Not to pick on Amazon, but like anyone in this room who's building anything remotely distributed, test it on Amazon. Because I have never seen things fail the way they fail on Amazon. And if it runs there, it will run anywhere, I guarantee. Like seriously, take that one for a spin. I love, for the record, I do love Amazon fiercely. It's just that like, you know, I've never seen TCP connections like end up in the state that they can end up in Amazon. Like I still can't explain it. And I've talked to Amazon architects and they're like, magic, it happens. And I'm like, no, it doesn't happen. Like that's, TCP is a thing. Like it's supposed to deliver, how did you, anyway. It is much more difficult by definition when you distribute something to get a global view of what's going on, right? If you want to understand holistically what's happening as a service and now you're running in lots of different places, guess what? That's harder, and it costs something. Security is harder. You have more things running in more locations that can be attacked in more places. You have more copies of your data. You probably have more users accessing the system. You have more network endpoints, right? Security is harder. Security, distribution is an exercise in trade-offs, right? Security is a process, not any one thing, right? You're as strong as your weakest link. And so as you have more links, guess what happens? And managing the life cycle of your data, as a result, is naturally harder, right? And everything else about distributed computing. For folks who haven't done a lot of distributed computing stuff, go home tonight and read, ask Wikipedia to tell you about the two generals problem or something. And you're welcome. That's the next hour of your life you'll spend sitting going, oh, that's interesting. But the thing is that we kind of understand fundamentally how to scale a lot of stuff, which is good, right? Which is why we're growing at the rate we're growing, right? I mean, we do understand load balancers and named services. We have been able to build really good kind of application level horizontal scaling. We have caches, we have content distribution networks, right? We have a lot of great technology down at the storage layer. We understand how to take arrays of disks and build that out to build increasingly redundant, resilient systems, right? We understand a lot of these pieces, which is really great. The reason I'm here tonight is because of the database. Because in spite of all those other things, the thing that is foundational to almost every application online is the thing that is fundamentally hard to distribute and make work in this cloud world that we're talking about, right? Why? Why is it so hard? A couple of reasons. I'm sure there are lots of possible reasons. I'm going to offer at least one view, right? You go back to the late 1960s, right? And there's this guy, Edward Codd, who's sitting around thinking about formalism for consistency models, right? And thinking about a programming model for data. So he comes up with a set of rules that is really, really pretty cool, really foundational and fundamental, right? And it's this kind of abstract calculus for how to reason about correctness of data. And then a bunch of people at IBM sit down and try to build something inspired by this. And depending on who you talk to, either they kind of got it right, or they were wildly off base, and Ted Codd was angry and never wanted to talk to the guys at IBM again. But basically, they went off and they designed this thing called System R. Right? And System R was kind of this very early first take at building a database based on SQL, right? And for those of you who are SQL people, you may love it, you may hate it. For those of you who are not SQL people, my personal feeling is that SQL has at least one true brilliant component to it, which is that it's declarative, right? You don't tell a SQL database how to go solve a problem, right? When you're doing MapReduce, you're kind of saying brute force, here's how to go do it. When you form a SQL query, you're saying, this is the problem I want solved. Use SQL database, you go optimize it. You figure out how to rewrite it, how to do whatever with it, right? I mean, this is what compilers do. This is if Itanium had been successful, which it wasn't because it was totally insane, but had Itanium been successful, that was the value proposition, that we're gonna do an even better job of that, right? SQL has this declarative nature, and that's an abstraction. That's really powerful. It lets you write your application logic and separately think about the database. So a lot of really good things came out of that early work. One of the limiting things was that just realistically, in the 1970s, not only did we not have much data, but we didn't have many places to put it. Disks weren't big, memory wasn't big, bandwidth wasn't a thing yet, really. I mean, there really wasn't a lot of capacity, right? And so what did they do? They said, okay, we're gonna come up with a database architecture where we're gonna essentially reinvent virtual memory. And maybe not reinvent, because that wasn't a thing yet either, but we're gonna do virtual memory, right? We're gonna take data, we're gonna chunk it into things called pages. So we're gonna lay out the data. We're gonna say a table looks like this, a row looks like this. We're gonna write that row, in order into memory. We're gonna map that memory directly onto disk. And guess what? Now it's really cheap to take that chunk of contiguous data and pull it up into memory. And it's the right size page so that it fits on a disk really efficiently, so that it goes through your cache lines really efficiently, so we can work with extremely, extremely limited resources. Really, really good idea in 1975. Probably a really good idea through the 80s and maybe into the early 90s, right? Fast forward today, that's fundamentally why when people talk about relational databases, they're still talking about vertical scale. They're still talking about getting that bigger box to handle more capacity, right? Because the optimization is all about that pipe between disk and memory. right? And that's really, really hard to scale out. I mean, you can try to apply caching, but guess what? Like, your caches aren't going to be aware of the transactional model, your asset model, or kind of your data model. And so it's going to break the consistency rules. It's going to break like what clients are trying to do in terms of interacting with each other. That's a real problem, right? It's also really hard to provide a highly available system at this point, because you've got this single pipeline. And if it fails, what happens? Right? I mean, you can try to make a copy. We'll talk about that in the next few slides. But like, that's problematic, right? It makes schema hard to evolve, right? So people hate schema because they're like, oh, schema is so inflexible. I've got to start out right from the beginning and decide what my data looks like. People shouldn't hate schema. They should hate the fact that this page-based model means that making any changes to your schema requires going through and touching everything on disk and moving it around. And so it's highly disruptive, it's highly expensive. Right? It's not schema that you all should hate. And I'm sure a few people in this room are like, no, schema. It's not schema, right? It's inflexibility of schema. Structure is good. Understanding like what your data is and how to work with it is a really good thing. Being able to work with it through different views and like dynamically change that schema and look at the same data from different points of view, even better. We'll talk about that later. But like, it's that rigid notion of schema that is so challenging. So this architecture, right, is inflexible. It is hard to scale out. It is hard to provide a continuous availability model around. It is hard to harness commodity, because by definition, what are you doing? You're optimizing around disks and bandwidth in a system that can like just scream through things. And that's why if you talk to like a seasoned Oracle person, they're all like, well, tell me about IOPS. IOPS, right? We've all been trained from the data point of view to care about IOPS. But cloud is not IOPS. Cloud is on-demand scale, and it's running things in memory. And those are contradictory ideas. So what have we done? Like, one of the things I think we're all really good at, like everyone in this room, whether you're a hardcore programmer, you know, whether you're someone who kind of plays with different computer systems, whether you don't identify as an operator or a DBA or a programmer or anything else, right? I think probably one of the common threads of everyone in this room is that what we do really well is pragmatically solve problems, right? Is recognize there's a thing we have to do. And if we don't have all the right tools for it right now, well, maybe eventually the right tool will be there. In the meantime, we have problems to solve. And we use the tools at hand to figure out how to solve them, right? So what have we done as an industry over the last 10 years? We've done the best we can with the tools we have to try to solve these problems. And a couple common patterns that you see, right? We've applied replication. We've said, run a database in one place, and every time you make a change, copy that change over to another place, right? Or, like, if you're really brave, like, do that in both directions, and hope that maybe you got it right. And I'm not going to go into the details of why that's a hope. All right, we're back. Lot of good systems built with this model to provide higher degrees of availability, to provide redundancy and safety, right? But anyone who's actually built a system around this knows where the challenges are, knows kind of what the contract is that you're making with whichever evil deity you fear. We can take the other approach, right? Sharding. Oh, you know, we should have saved a sock monkey. Who knows where the word sharding comes from? So everyone in this room kind of knows what sharding is, right? You take a database and you say, you know, I'm going to decompose it into 4 databases, and each of them has a completely disjoint set of the data, right? And now I can do like a subset in one place and a subset in another place. And that's why, like, you know, when you play your online game with your buddies, you may or may not be able to play with your buddies because, like, they may be on a different shard, and that's really frustrating. And then you're like, can I play with them? And they're like, yeah, it'll just take us a day to, like, figure out how to get you over there, right? The game industry is actually where this term came from, right? So you go way, way back to one of the first massively online game that people were trying to build, and those developers were pretty sharp, and they realized that their system was not going to scale. That they were going to have this problem where on day 1, they were going to get a couple users, day 2, they were going to get a few more users. You know, by day end, they were going to get swamped and the whole system was going to go down because one database couldn't handle it. And then again, this is like, you know, pragmatically, how do we solve problems? Some bright person was like, wait, I've got it, we're a game. We're going to write into the lore of the game that the reason people are playing this is there used to be one world, and it existed in the view of this gem. And then some evil force came through and shattered that gem into all these different pieces, shards. And so the universe was broken into shards, and everyone's going to play in a different place. And ideally, everyone's working towards trying to bring the gem back together. And of course, that was never going to happen. But it gave them, like, the semantics of the game gave them an excuse for doing this, which I think is just genius, right? That's just like the epitome of make do with what you can and figure out how to do. And the game industry is, I spent some time in that world, and it's just awesome because you do get to come up with all these incredibly creative, clever outs, essentially. And for the rest of us, we're like, yeah, sorry, you're not on the same like database as your friends, so like, you know, someone saw an update before they did. Like, sorry, you know. And that's what sharding is, right? It's this separation view of the world, and it lets you address more capacity. It lets you solve a number of real-world problems. It also breaks the view of consistency, because now you've got multiple databases, right? And you've got queries you simply cannot run because they cross these different shards, these different views of the world. Or you can run, but they're very expensive. And again, if anyone wants to, like, you know, brain teaser, go read about what XA is tonight, and, you know, go into your colleagues tomorrow and be like, I just read something awful that I want to unread now. We can also take a third approach, right, which is increasingly popular, and this is the one that kind of keeps me awake at night, which is that we can say, you know what, who cares about consistency? Let's abandon that. People don't really need that. Like, there are a few, you know, high-end applications that care about consistency, care about transactions. For the rest of the world, we'll just get rid of a model of consistency. Application developers are pretty good. They can probably figure out what to do. When there's conflict, they can probably sort it out. You know, when there are failures, they can probably figure out how to get back in the right state. You know, if someone lost a few dollars along the way, meh. Well, you know, I mean, seriously, like, I make fun of it and I laugh, but like, that is the world we live in, right? I mean, that is actually like a lot of systems that behave like that. Again, not because people are idiots, right? But because we're trying to do the best with what we have, right? We try, and I've done this. In fact, part of the reason I'm with NuoDB, I've been with the company now for about 4.5 years since we first started. And the reason is because I did try to do this a few times. And it just got increasingly frustrating and maddening having to explain to application developers or having to explain to myself when I wrote something that didn't work correctly what I'd done wrong. Finally I decided, you know what, no, I'm done with that. And see, here's the thing about consistency, right? By the way, if this was like one of the cool kid hacker conferences where you had to like write a certain amount of closure to even be accepted or something like that, this would be one of those slides with like a kitty with like big eyes going, like it has consistency or something. I don't do that. Like, I don't do the clip art thing. Or like if this was like, if we were channeling like James Nickens right now, right? This would be like one of his angry, like, sorry, people not know who James Nickens is? Okay, so you're all wasting time being here at my talk. Like, stay, because I'd like you to hear this talk. But seriously, go home tonight. Forget about the other stuff I said to read. Go home tonight and go pull up one of his talks on databases because they are hilarious. Also, he's really smart, but they're also really funny, and they're probably like pound for pound much more entertaining than this talk. I apologize in advance. But seriously, consistency, here's the thing, right? We spent a lot of time over the last few years convincing ourselves that transactions are these very special purpose things, right? I hear people say all the time, I have a few things that need transactions, but the bulk of my system doesn't need them. Right, transactions are complicated, transactions are expensive, transactions are whatever. Transactions are a thing that we invented to make our lives easier, right? Because they're a programming model that gives you consistency, right? But consistency doesn't mean transactions, right? Consistency is just a way of talking about the correctness of your data, right? It's a way of understanding something about the state of your data, about the state of it relative to other actors in your system, and when things fail, and again, things will fail like crazy in the cloud, what state you're in, right? In that previous slide, right, where I'm talking about sharding, right, splitting things into multiple different databases, there's still a consistency model, right? It's not as strong, maybe, as this first one, because you've got disjoint sets of data with disjoint sets of transactions, and if everything fails, you don't really know how each shard is left relative to every other shard, but there's still a consistency model, right? You can abandon transactions and still have a consistency model in a number of fashions, right? But when you get rid of consistency entirely, when you can't understand anything about the state of your system, right, that's when stuff fails at 2 in the morning and the pager goes off and like people are, sorry, pager, that's another one. Dial tone, pager, for those of you who don't know, there used to be this thing that you wore like right here and it would beep and you'd be like, oh, now I have to go like call, and all it would tell you is the phone number. It's like, go call this phone number, right? Which also probably had a dial tone. That was pretty cool. Right, so, but seriously, like I was talking with someone who works at PagerDuty, and he's like, yeah, our employees, like some of them don't know what a pager is. Like on day one, we have to explain to them, like, this is why the company's called PagerDuty. I was like, that's kind of awesome. And kind of sad. But like, seriously, this is the thing, like, beyond everything else, right? This is the thing that worries me that we're losing track of. It's not so much SQL. You can argue, is SQL the right programming language or not? I like it. NuoDB is a SQL database. You know, you can argue whether transactions and the way we've implemented them in SQL are the right model, or whether you want something that is a base model, or whether you want something that is kind of coordination avoiding. There are all these really interesting techniques people are playing with today, right? But at the end of the day, what you really want is you do want consistency. Because that's the foundation once you start to build everything else up and reason about what's going on in your system. And without a consistency model, without an ability to understand your data at any given point, there are all these crazy side effects, right? Side effects in terms of failure. Side effects in terms of what, like, I see and someone else sees, right? And I'm now going to cite the thing that everyone cites when they talk about consistency that's actually not consistent, which is ATM machines. But everyone loves to talk about ATM machines. And it's like, well, if you've only got $50 in your account, like, and you and your wife both go at the same time to take out those $50, how do you make sure it works correctly? And the trick here is that actually ATMs are non-consistent. Like, they are eventually consistent, they actually break this, but everyone loves to cite that example. So I'm going to cite that example and say, you want those ATMs to be consistent. But maybe you don't. Maybe you both want the $50. But I'm saying, like, then what's going to happen is one of you is going to get audited, you're going to get pulled in, it's going to be a mess, and like you're going to spend money that you don't have, you know, and then the economy goes down. So consistency. Sorry?
The bank is happy.
Well, the bank, someone is happy. Yeah, someone. Other side effects that happen, right? When we're not thinking about these models and we're starting to segment everything and split into all of these different views of the world. One side effect of starting to take a database and decomposing it into all these different pieces that you can't reason clearly about is that you get applications that are tied to your deployment model, right? So if I take a database that is one database and I split it into two shards and I say, like, you know, A through L is on one database and M through Z is on the other database, right? What's just happened? I've now had to change my application logic to understand that. And if I want to change my database, I've got to change my application logic again, right? Hence, DevOps. Okay, now, so here's the thing. I'm actually a huge fan of the idea that developers should appreciate the pain that operators live through day in and day out. And I'm a huge believer that operators don't appreciate enough how hard it is to write application logic and should be fluent in certain languages. So, like, philosophically, a lot of what comes out of the DevOps movement I really love, because it really forces people to understand the world in which they live. That said, I kind of feel like the fact that we've had to go into this world is really problematic. And in fact, recently I was giving a talk, and it was early morning, it was a breakfast thing, I hadn't had enough coffee, and I actually went as far as to say that DevOps is a bug, which got a couple irate questions from the audience. I didn't mean that. What I meant was just simply that, like, why we have such a fascination with the DevOps movement is in large part because we have this tightly coupled application and operational model, right? And that's the thing that drives me crazy, right? Because it means that when the application developer wants to make changes, it's hard to do so. And when the operator wants to say, I just want to run in more places, it's hard to do so. And all those things we were talking about earlier, on demand, flexibility, all those things go out the window, right? And that's a problem. Failure handling is a problem. Reasoning about your system is a problem. You end up with more independent pieces that are harder to manage, are harder to get that global view around, and are harder to interpret when they fail, right? When you've got a system sharded into 100 pieces and 2 of those shards fail, and you want to bring them back online, like, what's the state of your service? Like, hopefully the application developer knows what to do with that. This is all about complexity, right? I said earlier, as we build increasingly complicated systems, what we want is we want the net result for this to be simple, right? And my fear is that as we build things in this direction, we're building more and more complexity, right? Can you solve problems by doing replication? Can you solve problems sharding? Can you solve problems without consistency models? Yeah, you can. And our industry is like one massive existence proof that you can do it. Is it hard? Is it expensive? Is it increasingly complicated? Is it at odds with everything we're trying to do in cloud architectures? And is it going to be a problem as we look at the next generation of problems we need to solve? Yes. Yes, and that's kind of my argument. And in particular, when I say next generation, this is an example, right? Global deployment, right? Increasingly, I talk to people where the baseline is not I need my system to be redundant on 2 machines. It's I need my system to be running in at least 2 data centers. Like that's the baseline. That's not like a nice to have. That's why you can talk later about whether you can expand to 20 data centers, but like 2 data centers, must have. Why? Right? The common one is disaster recovery. That's the one we've done for a long time. But increasingly, it's more about active use cases, right? It's not failover. I want to run in multiple places because I have users in multiple places. And I want all of them to experience low latency, but I don't want to give up consistency. I don't want to give up simplicity of management, right? That's kind of what I'm looking for. Increasingly, it's also because like I've got users in multiple places, and they tend to access different sets of data, right? My operational database that's storing, account information, Boston users tend to stay in Boston, right? New York users tend to stay in New York. Occasionally, we travel to each other's cities, and we try to be polite about our various sports teams and whatever else, but like, and I throw out the word wicked a few times just to remind everyone where I'm from. But it's, that tends to be the case. Why should I pay the actual cost, like not theoretical cost, the actual cost of transferring data between different data centers, right? If you run on Amazon, right, it costs you money to move data from disk in California to disk in Oregon, or to disk in Virginia, or over to Europe, right? I mean, that's actual money. And if you don't need to move the data around, why do it? Or more to the point, you may not be allowed to, right? Amazon this fall opened a data center in Frankfurt, which is one of my favorite things they've done in a long time, because one of my favorite topics is data residency. This is something I'm really, really working hard on. If anyone in this room is interested in talking about this afterwards, I'd love to bore you to tears with everything I'm thinking about there. But like in Germany, there are all kinds of laws now that like a German citizen's data has to stay on disk in Germany. Like it doesn't matter where in the world they're accessing something, it's got to be on disk in Germany, right? Go ask anyone at Microsoft how they feel about the fact that their Irish users' data are in Ireland, right? And go, if you haven't like come across these use cases, go read about this, right? These use cases about where data lives and how it's accessed are fascinating. And this is a really important use case for why people want to run in multiple locations. Global deployment is kind of by definition, among other things, a trade-off between latencies and safety, right? We all understand that physics is in play. There's no like one database that's magically going to make all data consistent in all places simultaneously until we have quantum machines, and then a lot of us are going to be kind of out of a job. So hopefully that doesn't happen like right away. But like, that is true. But that said, that's the thing that we want to be able to understand in these systems. And the way we get that is, again, it's a different architecture. Cloud poses different challenges. The kinds of use cases we care about in these architectures, like global deployment, have different requirements and pose different challenges. And we can't just retrofit the stuff that we've been doing for 10, 20, 30 years in the client-server world into this distributed world. Because to solve this kind of thing, what we really want is we want to be able to say a data service, right, exists as a service you can access separate from the concerns of how it stores information. That's how you start to solve these problems. And again, that means that the database is not the disk. This is another one of these slides that would have like, I don't know what clip art, something funny would be on here, right? And everyone would be like, it's another internet meme. And if y'all want, I can like take a break right now and try to find the pictures. But I mean, you get the idea, right? Is that like, the database is not the disk, right? We've thought for 40 years of the database as the disk. And the database is not the disk. The database, the data management system, DBMS, whatever it is you want to call it, the database is the place where you get your information. And it consists of a service that you can interact with, and it consists of data, right? And when you start thinking about those as separate concerns, you start to understand how you actually address some of these cloud scale problems. But the thing is that we all think about the database as the disk, right? And like we do too. So here's a slide taken right from our marketing deck at NuoDB. You can tell it's from NuoDB because it's like fabulously lime green. It's got birds all over it. And it's got a lot of disks on there because we all kind of understand that when we put a disk on the slide, people kind of map that to be like, oh yeah, that's the database because that's the disk. Got it, right? So I mean, we do this too, right? And by the way, this is kind of another way of looking at what I was talking about earlier, right? When we think about database architectures, and we think about kind of how we've tried to take client-server models and distribute them, there are a couple familiar patterns that we've done time and time again, right? One is what we call shared disk, which is exactly what it sounds like. like make the disk bigger, whether it's actually a bigger disk or whether it's a disk array, you know, whether it's like some big, huge, complicated thing from EMC or NetApp or something like that, but like essentially scale by making the disk have more capacity and then have a lot of tightly coupled clients around it. We've also scaled using shared nothing architectures, which are not the same as sharded architectures. Sharded architectures are probably an example of that, right? But shared nothing is that idea of saying split things apart, right? Totally different view of the world. But again, still focused fundamentally on the disk, right? I was having this conversation with someone beforehand. We were talking about Hadoop, and we're talking about MapReduce, right? Hadoop is a wildly powerful and popular technology. It solves a lot of really good problems, right? But what is MapReduce? MapReduce is a like, chunk the data up into a lot of places, put it on a lot of individual disks, and then send work to where that data lives on disk, right? And as a side effect, yes, you get to take advantage of the memory and the CPU that's co-located with that, but it's still focused on where does the data live? Where's the disk, right? Google, for those of you who haven't read the Google papers, the Spanner and F1 and someone's gonna have to help me. What's the one? What is it they built on top of F1? There's a third one. Go read them. They're actually really interesting papers. Google, you know, a few years ago basically stood up and said, we know we were kind of the spiritual parents of MapReduce and this whole NoSQL movement, but it turns out like we can't do AdWords without SQL. But we can't make SQL scale because it's all this client-server stuff. And so what we decided to do is build this whole new database around a synchronous commit model. And as the name implies, synchronous commit essentially means that you have some notion of global consistency at the cost of latency. That's what synchronization is, right? And how does Google solve it? They bought a whole lot of atomic clocks. They built a whole lot of very special purpose high-speed networks. And they took the schema and they chunked it up in such a way that typically, you know, you can run things at pretty good latency. That's great if like you've got like piles of money and you really don't know what to do with it, and you're like, let's get a lot of bespoke hardware and build something that solves a very few specific problems. It is an amazing piece of technology. The papers are remarkably readable. I really highly recommend going and checking it out. The thing is, most of us can't do that. Like I know I don't have like a atomic clock sitting around, much less the thousands that Google has deployed. So for the rest of us, you know, there's this idea of how do you build these architectures that do all the stuff I'm talking about, but address these challenges that are inherent in trying to build these systems. Some time ago, we decided to come up with a term to describe this because we kept talking, you know, people kept saying, are you shared disk or are you shared nothing? Or maybe you're synchronous commit. And you kept saying, no, we're not any of those things. We're like, well, what are you? You know, this is like that you know, Eddie Izzard has this comedic routine where it's like, you know, people are already living somewhere and then like colonists show up and they plant the flag and they're like, I took your land. And they're like, you can't take my land. They're like, well, do you have a flag? I don't think so. So now it's my land, right? So it's like, if you don't have a name, you can't be an architecture. So we stepped back and tried to think not just about what NuoDB is, but what is it we're talking about with all of these kinds of systems we're trying to build. We came up with this thing that we call the durable distributed cache. And it's interesting, this has been like a slide we've used for ages. And a couple of weeks ago, someone actually was like, hey, Seth, is that a thing? Like durable distributed? And I was like, yeah, it is. And they're like, really? I've never heard of it. I'm like, that's probably because it's like not a thing we talk about kind of in detail. It's just like how we talk about our architecture. And they're like, well, what does that really mean? You know, I was like, all right, well, let me explain what it means. So let me explain to you all what it means. It's not about our product specifically. It's about kind of the kind of architecture that I think you want to address these challenges. The durable distributed cache. First part of that is the word cache, right? Lots of things run in memory, right? But what I think you want in a modern architecture is you want the database to run in memory. You want an in-memory database. What do I mean? I don't necessarily mean all the data has to be in memory, right? Whether you decide to hoist all of your data into memory or whether you just have some small subset of it, that's a separate question, right? But you want the database, you want the service to be something running in memory, right? Not just because that gives you memory speeds, although obviously that's good because memory is faster than disk. Well, at least for the moment, kind of as memory and disk start to blur, that's less true, but we'll take that just for the moment that memory speeds are good. But when you're running in memory, there are all kinds of optimizations. You can start to think about, again, that you can't deploy when your focus is on IOPS and about how quickly I interact with a disk, right? What are the characteristics of a cache? Right, everyone in this room has probably interacted with some kind of cache, whether it's like memcache or whether it's varnish. whether it's some kind of custom caching technology you pulled into your database, into your application. I think a cache has a couple of important properties. It should be transient, right? Shouldn't be durable, shouldn't be like safety for the database. It should be able to fail. It should be able to come and go. It should be a thing that you populate on demand as you need information, that you can drop from when you don't need information anymore. I think caches should act independently, right? I think you should be able to say, I'm caching information in different locations, and that's fine. I don't have to rely on the fact that, like, you know, my record can only be in cache at a given place, right? Because that gets you right back to this notion of what happens when that place is unavailable, right? Or what happens when I want to put my information somewhere else for a specific reason. Caches naturally support hierarchies, right? We all talk about memory and L1 and L2 and whatever and whatever and whatever and disk, right? And again, like those lines are getting blurred today, and like everything has, you know, hidden caches in it. And like people don't trust disk drivers because disks now have like caches in them, and you never know when you say write something to disk, is it on disk, right? That's like this existential mystery that database people love to get worked up about, right? But caches are everywhere. Hierarchies are everywhere. Hierarchies are really good because they inherently take advantage of kind of what's interesting and what's not interesting. They optimize naturally the things that you're working with at any given time, and that makes a lot of sense. Like, I want that in my cache. And perhaps most importantly, a cache should comprehend service semantics, right? So when I run Postgres and then I put memcache in front of it, right? I may have just accelerated the ability to get at data, but I'm not programming to memcache with the same model that I programmed to Postgres, right? Ditto if I put, it's not about SQL, right? I mean, I could put a cache in front of a key value store. And if that key value store was more than just a key value store, if it had some notion of transaction consistency, right? The cache doesn't. And so I've just broken something about the way I'm supposed to interact with the service, right? So it's not just about a cache that I layer on as an afterthought, right? When I say a database in the modern world should be something in memory, I really mean like the database is the thing in memory. The database is the cache. The cache is the database, right? This is how you interact. This is the service endpoint. And I think it should be distributed, right? So I said earlier, I was going to give you my view on what distribution means, right? A distributed system, that's a term we throw around a lot, right? We like to talk about distributed meaning like it's running in multiple places. It turns out the term distributed system actually has a specific meaning, right? And if you go read like, you know, your CS whatever book, a distributed system is a system composed of independent actors that coordinate via messages, right? What does that mean? It means you have a bunch of things that run independently. It means they can all do the same kinds of things. They can all take on the same workloads. They can be started independently. They can be stopped independently. But for the things that they share, they have to know how to coordinate with each other, right? It's not a shared disk model. It's not some, you know, magic. It's just that they have to be able to talk to each other, right? This is a view of the world that promotes resiliency, right? Promotes continuous availability. Promotes the idea that you can lose things and add things kind of arbitrarily at any point at any time, which is that whole thing about cloud, right? That's what we want, right? Is on-demand capacity without having to think about how it impacts anything else that's running. And that distributed system is made up of a whole bunch of pieces, but it should define a single logical service, right? That's really that abstraction, that ability to say a service is made up of a whole bunch of things, but it just looks like a single thing, is how you insulate your application, is how you build towards simplicity, is how you build a system that will survive all kinds of crazy failures. So, you know, again, not a new idea for anyone who's ever done like peer-to-peer programming when that was like hot and everyone was talking about, oh, it's a peer-to-peer system, right? That's what we're talking about, peer-to-peer system. And if access is, you know, supposed to be in memory, then access is via peers that are running in memory, right? And you should be able to scale those independent peers to be able to solve separate tasks. It is a cache. It is paired with this caching technology, so you can optimize not just around the fact that you're in memory, but now because these peers are independent, they might be doing different things. Different users are interacting with different peers. What does that mean in the world of caches? It means affinity patterns start to naturally emerge. That's what caches are, right? They're going to naturally start to bring certain things into memory in one place, certain things in another place, and that's what you can start to optimize around. Not just the fact that it's fast because it's in memory, but you can start to take advantage of those patterns, right? That's how you build a system that really takes advantage of cloud and scales. Durable. I'm going to argue that almost every data system wants to be durable, right? And what do I mean by durable? I mean Like if everything shuts down, you should be able to restart it and like your data is still there, right? That's a good thing. You can build systems that are purely in memory, right? And just have so many different replicas running in so many different places that you can sustain failure, and there's a really good chance your data is still there. And for some systems, that's fine. But I'm going to argue that like most of us really want to know that data is written on disk. Like, and actually, like most of us take this to an extreme. I've got like 9 backup drives sitting at home, each like with a subset of my various laptops and desktops, and like technically that's really durable. But if I actually had to go find anything, I'd be in a lot of trouble, right? So you want durability, but you also want some like rules about what that is. If access to a system is in memory, right? If the database is in memory, and that's where you're interacting with the database, and the database is no longer the disk, right? Then that storage level, that durability, is no longer about how do you get performance in a system, right? That storage level is now about safety and it's about availability, right? Safety, system can crash and I can get my data back in the correct state. Availability, like if I need something and I don't currently have it, I know I can go there to get it, right? It is the complete set of my data. Freeing yourself from the optimizations about disk I/O is what I said earlier is one of those things that has hindered us in terms of client-server architectures, right? Why? What does this help us with? Like, why do you care, right? You care because if management is operational, right, you can manage things like storage and redundancy and replication, and when you need to upgrade a disk and when you need to move things around, you can do all that totally independently from how you've written your application. Right? And again, that gives your application developers the chance to go off and do whatever they want, and your operator can sit there all day and complain about the fact that the disks are filling up and you've got to replace them and you've got to swap in whatever else, and it's not disruptive to the running application. Right? And that's really where we start to get the promise of everything we're trying to do. It also lets you then think about layout to address different challenges. Right? I talked earlier about why you want global operations. There are different kinds of problems you want to solve. Some of them are about performance. Some of them are about just simply managing the data. Some of them are about ensuring that data is known to only be in certain places or not be in other places, right? Lots of different problems you want to be able to solve. If your database is predicated on the idea that data lives in a particular location because that's how your system runs, you can't make those different choices application to application, right? Which means you can't really solve different problems on the same kind of cloud commodity architecture. And this does get you to commodity. Right, because now we don't care about massive disk arrays, right? It's about safety of data. It's not about raw IOPS. And you can now, the one thing you do need to think about is you need to think about how those in-memory pieces work with that storage tier, right? But you have flexibility. You can decide, is it about case safety? Is it about synchronous replication? Is it about writing in one place and eventually things will move around? You can decide what those problems are you want to solve, but again, it's not going to affect what the application sees. All right, so I started out talking about cloud and saying this was all about cloud. This was motivated by kind of what's going on in the cloud world. So how do I get back to that now that I've kind of gone off on this deep philosophical view of the purity of what I think we should be building? Cloud requirements, right? What did I really say in the beginning? You want to be able to do scale on demand. You want to be able to provide continuous availability. Right, you want to be able to simplify application and operation. You want a single logical thing you can program to, a single logical thing you can manage, but you don't want your operator and your application developer to have to be commingled, right? You want independence there. You want to be able to run hybrid. Hybrid means heterogeneous infrastructure. It means running in multiple locations. It means running in different environments with different requirements, and probably hybrid workloads. Right? Everyone today wants to get at least a little bit of analytic insight out of their operational systems. Right? Traditionally, that's a really hard problem. Right? We're getting a lot better at that. That's a thing we do at NuoDB pretty regularly with people. That ends up being a challenge for a lot of systems, and it's a challenge because systems are designed to do one thing or the other. You want a thing with clear failure semantics, and you want to operate as a service. You don't want to think about lots of random things. You want to think about a service. And I'm going to argue that anyone in this room who's thinking about public cloud, private cloud, hybrid, OpenStack or Amazon or kind of any other view, or just simply running a whole lot of virtual machines, right? Most of you have most of these things on your checklist about ideally what you like when you're thinking about your foundational, platform systems. And this is what we were just talking about, right? To get to these things, you need to have stepped back and thought about these core architectural ideas. Now, can we solve some of these things kind of today? Can we hack together stuff and do replication or sharding? And can we kind of, you know, build wrappers around things and expose some things to the application? Sure, we can. We can do that. It's hard, it's painful, but we can kind of do that. What we can't do are the things that are the next round of requirements that everyone is starting to ask about, right? And everyone I talk to today, when I come down here and talk to people on Wall Street, what everyone is asking is the same set of things. Great, I understand all those things, but the real reason I'm moving to these cloud architectures is because of the promise they have to be able to do all of these new things that are incredibly important today in a global world, right? That global operation, that ability to be active in multiple places and still have a clear consistency model. That data residence problem of being able to understand exactly where your data lives and speak with confidence that you actually were meeting regional requirements correctly and that the audit proves it, right? The ability to run a system in an automated fashion where it's driven from policy that is your SLA, right? You're saying, this is the problem I want to solve. My database is a service. It's a collection of things, but I can treat it as a service and I can drive it in an automated fashion so that that's not the thing I'm spending all my time on. The thing I'm spending my time on is writing my application, and I have a service that gives me the on-demand capacity I need when I need it and doesn't use it when I don't need it. You only get that when you drive things from policy, and that's why everyone who's building kind of modern infrastructure as a service is thinking first about how do I drive things from policy. You want the same thing from your data management system. And multiple models, right? Everyone is running more than one database because they have some data they want to think about in a relational format. Some things are documents, some things are graphs, some things are key values, some things are big data. And, you know, now we've got data lakes where we're just like throwing everything in there and hoping that like they can swim, or like whatever the metaphor is. Data lake is my least favorite new term, but I kind of appreciate what we're trying to do with it. You know, the reason we have all these different things is because it is very hard to handle those multiple models in one database. And that's not because it's hard to like put different front ends on a database, right? I mean, you can take a SQL database and say, now be a graph database because I put a Sparkle front end on it. You know, Sparkle's like the worst language ever, but like it's standard and it works pretty well. It solves really good problems. But the hard part of graph is not Sparkle or implementing RDF or some other standard. The hard part of graph is that fundamentally it's a different set of questions you want to ask that you optimize in a different fashion, right? Why do people care about the database being column or row? Because they understand that there are different questions you will ask, and one of those is really well optimized to answer one set of questions and the other one the other. Why? Because again, all of those things, are you row or are you column? Are you graph or are you relational? Those all come back to how do you store your data on disk? That's the gating thing for all of those, right? And when you're not about disk, when you're thinking about architectures that are all about getting data into memory, because that's where the database is, you can actually think about these multi-model problems in a fundamentally different way. Here's the one slide. I'm going to show you what NuoDB is. And my time is basically up, so I'm not going to spend a lot of time talking about this. But when you look at NuoDB, we are that thing that I've been describing. We are a distributed peer-to-peer system that is in memory, but is also durable, is designed to scale on demand, to run in multiple locations, to be able to address all of these problems and provide to both the developer and the operator what looks like a single logical system. Standard SQL, you know, joins, views, schema, but flexible schema, because we don't care about representation on disk. You want to add a column, you want to change a column, just do it. It's not touching anything on disk, because we don't care about the format on disk. We just care about how you interact with it in memory. Summary. Cloud is hype. Definitely, like, huge hype curve around it for sure, but it's not just hype, right? It's really identifying, I think, a new set of architectural views and problems that people want to solve. And when you think about the foundational services that sit on top of these kinds of models that let you exploit all the things that, whatever you want to call it, cloud or scale out or horizontal scale, yada, 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 all the things you want around on-demand capacity, around continuous availability and global operations and like simplicity in the face of running in, you know, hybrid or heterogeneous environments, right? Those foundational services need to be built assuming that that's the stuff you care about, right? Or they're just not in the end going to be able to give you what you want. Extending that and having services that actually can provide a global consistency model, again, not talking about transactions per se, not talking about SQL, whatever, but a clear, consistent view of your data. We are transactional in SQL, but like putting that aside, That's what's going to make this thing work and be simple, right? And when you have simpler systems, those are going to be easier to scale. They're going to be far more resilient, and they're going to let you move to what everyone is trying to move to today, right? Which is that global view of the world, global operations, where all of these issues get magnified, where latencies suddenly are much harder, where failures are suddenly much harder, where security models where you've got users from all over the place suddenly are much scarier, right? If you're interested in reading more about NuoDB, I could point you, obviously, NuoDB.com is our website. dev.nuodb.com is the landing page to go find our documentation, to read about what it is we actually support. We have technical blogs, white papers, piles of information in there that I think is actually pretty interesting. With that, I just want to say most of you stayed, and most of you stayed awake, and I really appreciate that. Thank you to everyone, and thank you to Eric. This is... I was going to say, this is actually 2.5 years now. I was looking at the calendar that we've been coming down and doing this, and we've talked a lot about this stuff over the years. But it's always fun to come down here. It's always really interesting questions, and so I don't know how much time we have before we get kicked out, but if we have time, I'll take a few questions.
Okay, before we go on questions, I want to give a great big thank you, Seth Proctor, NuoDB CTO. We are going to be giving away this drone very shortly. The bucket to throw your business card in is right there in the back, moving it around. There you go, he's holding it up. Moving it around the room. If you don't have a business card, please design your own business card on those little sticky notes in the bucket, bowl, whatever you want to call that. It's somewhere in between. And the other thing I'd like to mention is if you've taken any photos here tonight, please post them to our meetup page. Everybody here should be a member of the New York's SQL NoSQL meetup, so you should be able to post them to the page at the end of the event. I just noticed that meetup doesn't let you do it until after the event is over. But in any case, you can all post your photos out. And we got t-shirts here right at the end of QA, right after the raffle. Everyone is welcome to come up and grab them, but we have exceeded room capacity by quite a lot, so we probably don't have enough shirts, but hey, whoever gets them first. So let's start with the first question. You are very excited to get your hand up. You get the first question.
Can you go into a little bit of detail about durability, cache, and durability guarantees and how that technology is working?
In NuoDB specifically, or kind of like general? Yeah, sure, I'm happy to. So NuoDB fits this model I was talking about, a peer-to-peer system where there are some peers that are focused on running in memory and other peers that are providing durability for the database. And in particular, in our system, you can have kind of an arbitrary number of both. And they're completely independent. So you can have in-memory peers, they all can do the same work. Part of what we spent a lot of time doing is optimizing how those in-memory peers work with each other so that you have that property kind of memory hierarchy and you can work really efficiently with things in memory. The really interesting question becomes, when I make a change in memory, how do I make sure that's reflected in the durable state? Right, so that if the system fails, or even worse, something, a sub piece of the system. It's really nice when the whole system fails. That one's really easy. That doesn't happen so often in real life. More often, like something subtle happens in a piece of the system. We provide what we call a commit protocol, and this is very similar to what you see in a traditional database, where you can say, does commit mean I've written it to a kernel buffer, or does it mean I've actually written it to the disk, or have I written it to the disk and read it back? Again, because disk controllers lie. Damn disk controllers. We provide the ability basically to say, when I make a change in memory, here's the simple version, and then I'm happy to go through the more complicated version later. Simple version is, when you make a change in memory, asynchronously, we'll send that change to all of the peers who care about it. Right? That's that contract about messaging between peers. We let you essentially decide which subset of those durability peers have to get pulled into the synchronous path to acknowledge back to a client that the commit has succeeded, right? So it's not tweaking consistency. It's not like eventual consistency of some kind. You are consistent at the moment you commit, right?
So
the question,
you're waiting for a quorum, and then you're...
Well, you can choose. You could say, just broadcast it to everyone in memory, done. You could say, broadcast to everyone in memory and make sure at least one point of storage acknowledges that it's written to disk, or two, or n, or one data center, 2 data centers, 3 data centers.
So depending on So there's a hit of performance if I enable the durability of the system, all right?
There's almost no hit in performance if you enable the baseline of durability in the system. What you get to choose is, as you scale out your system, is that enough for you, or are you more conservative, right? As you choose to write to more locations that are further spread apart, right? Think about a database running in 3 continents, right? Your commit protocol could be, make sure that it's written to disk in at least one place on all 3 continents before I acknowledge commit. That's a choice you can make, right? Obviously that's high latency, but it's extremely safe. You can also say, make sure it's written to my local data center synchronously in one place. It will get written to all the other places, right? And in the case of failure, it will always be reconciled correctly. That's our contract to you. We can't violate that or we wouldn't be an asset database, right?
So my last question, so if resolution, if it doesn't satisfy the contract, I as an application developer then have to deal with.
Well, you as the application developer, again, you don't see any of this. Like, I'm an application guy, and so I sympathize with people writing application logic. I don't want to have to worry about this. I want my operator to decide, like, this is the rule. Like, I deploy this database for 15 applications. Some of them, like, essentially need no durability. Others are super conservative. And it might be the same application, but different users who are deploying it need a different contract in a given deployment of it against a different database. So it's an operational aspect. It's not embedded in the application. Okay, another
Next question.
Yes.
Yeah, so I have a question. So there is a Hazelcast technology, and could you please explain what the difference between the distribution mechanism in NuoDB and Hazelcast, and if there any difference?
There are some pretty substantial differences. I'm not going to try to go into all the detail here for 2 reasons. One, it will take too long, and 2, I'm sure I will get it wrong. It's been a few years since I was deeply, deeply familiar with Hazelcast. It's been longer still since I actually tried to program to it. You're right, Hazelcast is another system that would have similar characteristics, right? That is designed around distribution, that is designed around being able to coordinate at a caching tier. Obviously, it's not designed with the kind of SQL semantics that we're designed for, so that's an important difference. It's not designed for kind of the arbitrary operations in terms of length of transactions, in terms of scope, in terms of how things interact. You know, it's not designed with the same notion of global scale out. I think Hazelcast is, you know, again, I don't want to talk a lot about it because I'm going to get it wrong. I mean, my memory of the last time I did anything deeply with Hazelcast was that it was very powerful for doing kind of specific caching scale out applications, and I think that's probably still true today.
Okay. Yes.
What was the name of the individual you mentioned we should all look up his stuff?
James Mickens.
James.
He's a researcher at Microsoft, yeah, actually, specifically, go try to find the talk that that he gave at Monitorama. I saw the longer version of it at the MIT Database Day about 1.5 years ago, and like it was like 35 minutes that I didn't stop laughing. I mean, it was when he starts doing his like Bane impression from Batman, like rallying the troops around NoSQL. Like I lost it. I mean, it's real brilliant. I highly recommend it.
Can you repeat the name again?
Mickens. And
yeah. Can you touch on what is the difference between NuoDB and Spark, the Hadoop ecosystem in memory database?
Sure. I mean, Spark. I really like what Spark is. I mean, I think Spark is a really good technology that comes from, unsurprisingly, because it comes from a group at the AMP Lab that is doing just some next generation awesome stuff. The AMP Lab is also where a lot of the kind of next generation optimistic coordination systems and kind of conflict avoidance systems are coming from, which I also think are really fascinating. You know, the way I look at Spark is the way I look at a number of things that are trying to sit on top of the Hadoop infrastructure and ecosystem, right? Which is that, again, Hadoop is designed around kind of a MapReduce model. It's designed around this notion of you want to do very large batch operations, and so you distribute those to where you've got, you know, segments of your data stored. It's not so much about on demand, like I need more capacity right now, you know, because like if you look at traditional scientific batch scheduling, right? I mean, traditional batch schedulers, you might spend an hour deciding how to schedule a job because it saves you a day of compute time in that, right? I mean, that's kind of more the scale when people were thinking about these large scale systems. You know, what is Spark doing? Spark is doing something really smart, and they're saying, well, let's still do these scale out things, but let's get things hoisted up into memory. Let's run it, and that's more about memory speed than it is about optimizing how the peers coordinate with each other. It's still a fairly decentralized system, right? It's still kind of assuming something about the access patterns and where data lives on disk, right? So I think it's really more fundamentally about how do you provide someone a really fast, familiar model for doing query than it is for kind of arbitrary operational processing. But certainly, if someone came to me and said, I really want a Hadoop in my ecosystem, I'd be like, well, first of all, you want Hadoop. You don't want a Hadoop, but like, that is how I hear it. A lot of people are like, well, I need Hadoop. And they're like, good on you. Well, let me know when that Hadoop arrives for you. I would definitely tell them, like, Spark should be on the like short list of 2 technologies you look at. Yes.
So did you just disprove CAP theorem?
No. Okay. No, I did not disprove CAP theorem. For the record, no, I did not disprove CAP theorem. CAP is again, in that spirit of distributed systems are about trade-offs, right? CAP is a really good, sensible formulation of the idea that when you scale things out, there will be trade-offs. And you really have to decide, like, when things fail, do you care more about the correctness of your system? Do you care more about, you know, being able to get at a system in all places? Like, by definition, if you're running in 2 places and the network between them gets cut, right, you have a choice. You can say, well, if I keep running in both places, I can keep running, but there's a chance for my system to diverge, right? Or if I don't keep running, I have to shut something down, right? Now, in a distributed system, if I choose to shut down half of that, is my service still available and able to address all the same data? Yes, it is. Right, and in CAP, the formal definition of CAP is that all queries to the system must have responses, right? And that's why it violates that notion of availability. In practice, do most of us care about that formal notion? No, we care about the service being largely available, right? What's interesting about that? Well, what's interesting about that is that consistency is only violated in that network partition case if there's a chance for the same thing to be updated in a different way on both sides of that partition. Right? And again, this comes back to, like, it's not about, you know, pedantic notions of transactions or SQL or whatever else. It's about what is the consistency model, right? You can construct a consistency model where you say, I'm going to allow changes to happen on both sides in a way that I know how to reconcile them later. Google Wave is a great example of this, right? People largely gave Google Wave a pass because, like, it was this brilliant core technology with this awful front end, and Google did what they did with like 90% of their stuff. They threw it over the wall for a year and then they killed it. But if you go read about what Google Wave was under the cover, it was essentially a thing that said, it's not eventually consistent. It is consistent. It's just that at any given moment in time when you observe it, 2 things may be out of sync. But the programming model is such that we know that those changes that are out of sync will always eventually have been consistent relative to each other. I think I did that one correctly. And so you can always put the system back together. And I think that's, certainly philosophically, that's where we're thinking and we're taking our software. I think there are lots of different views on this. You know, I think that CAP will always be a useful kind of reality check and way of thinking about systems, but I think as systems evolve and they become increasingly global and distributed, we will have to think more about the subtleties, and it'll go beyond kind of, is it about CAP, but where do you fall in the spectrum in terms of the problems you're trying to solve.
All right, we're going to have time for a couple more questions, but before we do, has everyone had a chance to put their card or information in for this drone? Anyone not, raise your hand now, because I'll pass the bowl back. No, okay. So we're going to raffle this off very shortly. We'll take a couple more questions and raffle it off. Yes.
So the architecture you described is pretty similar to the one Elasticsearch is using, you know, on top of the distributed cache and the eventually consistent model. How do you, so it's like 2 questions. How do you route the calls to one shard or the other? How do you decide which one it is? And if you in fact the change in 2 shards at the same time, how do you handle conflicts?
Well, the answer to both of them is kind of the same thing, right? Which is, again, we don't think about sharding, right? There's no notion of sharding in NuoDB. What there is there's a model where the database is in memory. It's running across a collection of peers that know how to coordinate. And at any given time, data may be sitting in more than one cache. And when data is sitting in more than one cache, it's up to those peers to do what any distributed system has to do to coordinate between them and make sure that we are not violating those rules of consistency. You're right, there are similarities to Elasticsearch. There are similarities to some other similar systems. You know, Elasticsearch, I think, is fundamentally different because it is thinking about more that kind of, maybe it's not sharded, maybe it's partitioned because it's not as, you know, directly visible. But that is how it's thinking about the model, and we're thinking about something in a fundamentally different fashion.
I'm sorry, maybe the question was wrong.
Okay.
How do you reconcile those changes? Because if I make a transaction and I hit one memory, one data center, if you want, and I
So
make the same change that is non-compatible.
The answer, I don't want to sound flip. The answer to this one takes at least half an hour to go through.
Okay.
So I'm going to point you to our white paper. The really short version, right, is that if you have something in cache in 2 places and you're making a change in one place, part of what our system knows is exactly where something is at any given time. And so it knows that, like, there may be 100 nodes that the database is made up of, but there are only 2 places in memory where that object is sitting. And so it knows that those 2 nodes need to coordinate with each other to ensure that the change is valid. Of course, what that means is that if something's only in memory in one place, then coordination is entirely local. And it means that as you scale it across geographies, if things tend to have locality to geography, you're land local in terms of the changes you're making.
We have time for just one more question, but Seth will be here for one-on-one questions afterwards, so you've had your hand up a while.
Yeah, thank you. Based on your presentation, but I see that scalability is one of the bigger feature of NuoDB, and this is the one of the reasons NoSQL is being used for a long period of time. So my question is this NuoDB is challenging that one, because in NoSQL we have to lose ACID properties, we have to lose joins, all those features we have to lose of relational database. Are you saying that NuoDB is an alternative to the NoSQL?
For sure. I mean, I think you know, the way I look at it is we went through this whole client-server world with relational databases, right? And then we spent a long time doing NoSQL systems, you know, partially ACID systems, eventually consistent systems, sharded systems, because they help solve these problems, right? And I think that 10 years ago, if someone had stood up, we may not have the right answer, right? But if someone had stood up and said, I have an answer that lets you take Oracle or Postgres or whatever and run it on 100 machines and nothing changes and your application still is a single connection string, I think most of us would have signed up for that. Been like, yes, that's great, now I can keep going, right? We've gone down this path of doing these other things because they're the things we could do. So yes, you know, we're certainly doing something that I think is for some NoSQL people makes their life a lot easier. For other people, NoSQL is not about scale, it's about a simpler programming model, or it's about, you know, there are lots of different use cases for it. We have actually more users who are traditional relational database users today, who are saying, I'm an enterprise and I need to get that thing that I've been doing into the cloud model. But we also have people who are saying, you know, I tried Cassandra, and I really liked that ability to scale. I didn't like losing consistency. I didn't like losing my SQL model. I didn't like losing whatever else. So yes, I think it's less about competition. It's more about kind of the, you know, understanding what the problems are you want to solve, and understanding kind of where you want to put effort.
Okay, Seth will be here for one-on-one questions. We're going to raffle off this awesome drone. Well, after the raffle, feel free to come up, grab T-shirts. Thank you, Seth Proctor, CTO of NuoDB. Just dump out the notepad from there. Borrow your laptop space. Please. Can I ask you to mix this up? Oh, come on, mix it up better than that. Look in the other direction, reach in and grab a card. Look in to there, reach in, grab a card.
Definitely class. And wolf, just both.
Oh, she's picking them out. Oh, that's 2 there. Wait, you gotta pick one. Okay. Read it out. And the winner is?
Mark something. Is it Mark or I don't know. This is Mark, right?
Mark
That's Mark.
Suits?
That's
No.
me.
That's
No
you.
way. That's me.
All right, man. Congratulations. Guys, come up for a crowd shirts. Thank you all for coming.
Thank you so much. Really appreciate it.